Good morning, good afternoon, good evening, everyone. Welcome to our first knowledge sharing webinar in the 2025 IEEE Metaverse Grand Challenge Series. It is a platform exploring how simulation-based learning and immersive technologies can drive real-world impact in sustainability and smart city development. Today, we will mainly focus on smart cities and SusTech theme category application process. I am the competition chair of 2025 IEEE Metaverse Grand Challenge for simulation-based learning. If we look at our session agenda, firstly, we will start briefly what is our challenge objective and what are our theme categories. And today, we will go through the process to just want to discuss the SusTech and Smart City thematic category application process. Today, we have an invited speaker, Jessica Sweeney. She will present her talk about the simulations as catalyst for sustainable smart cities. Looking forward to her exciting talk, actually. And then we will go to the process to discuss how to prepare submission materials and also to understand evaluation criteria. And we have also exciting news. We will continue our knowledge sharing webinar series. We will also provide that kind of info, and then we will go to the process to Q&A session. Briefly, I want to just cover that. What is our challenge overview actually? If you want to just reach more details, and please scan the barcode and check our website. You can just find each detail through the process. But here, I want to go to the process to discuss what is our objective actually. The challenge aims to enable simulation-driven learning experience on either 2D or 3D metaverse platforms. You can design, simulate, and showcase emerging technology elements using real-time additional technological process like AI, artificial intelligence, virtual reality, augmented reality, or XR. And also you can also adapt user adaptive simulations. These are the kind of the features how you can process to just implement your idea. The goal is here to create scalable, immersive, and global accessible education tools that transform our learning approach or mindset. In order to apply for the challenge, firstly, you should go to the process to fill out the express of interest form. Yeah, you can scan the barcode here, or just want to check our website. Please fill out the form as a first stage actually. Okay, what are the theme categories? You have a freedom. You can choose either including healthcare application in digital learning, advanced learning in educational or classroom environment, or smart cities, sustainable smart cities and urban innovation. Today, we will mainly focus on this thematic process. Here, the focus is to design engaging and interactive simulations that can enhance the learning and capacity building experience for young professionals and citizens actually. But I want to also just highlight here, you have a freedom actually. You can go to the process, design your idea for the challenge categories. Just briefly mention that what is the concept of the sustainable smart cities or urban innovation thema. We can invite you actually to simulate the future of urban living within the sustainable smart cities and urban innovation thema. You can go through the process to explore how immersive simulations can help design greener, smarter, and more resilient cities. You can choose either virtual sustainable labs or eco-innovation in action and public safety and resilience. What is the meaning that of the items? For example, for the case of the virtual sustainable labs, you can design interactive environments that demonstrate the key sustainable principles, like from carbon neutral design and green architecture to community-based resource management. These are the examples, but you can just design your mindset or your idea perspective actually. And for the eco innovation in action side, actually, you can simulate systems that model energy efficient buildings, smart grids, waste management, or urban farming actually. Here, that can help users understand and apply the sustainability principles or practices through the gamification learning approach. You should also just work on the public safety and resilience side actually, because that's also a critical part for the sustainability urban innovation thema. You should create the immersive scenarios for disaster preparation, emergency response coordination, or smart surveillance systems. Through that process, we can understand our awareness of the urban resilience and safety through the engaging training tools. These are the some elements you should work on that the topics. But I don't want to just spend more time here. I just want to introduce our invited speaker, Jaswini Chili Lukuri, actually. And it is my pleasure to introduce our distinguished speaker today. Jaswini is a senior engineer, uh, software design at Khatib and Aleme Engineering Consultants. With over 5 years of experience, Jaswini brings deep expertise in high performance building design tailored diverse climatic and urban settings. She holds a master's in building energy performance from Center for Environmental Planning and Technology University. Is known for integrating simulation tools and BIM technologies to optimize energy efficiency, daylighting, and thermal comfort. Her work bridges the technical and visionary, focusing on how digital workflows and simulation-led strategies can transform to build environment into more sustainable, intelligent, and resilient spaces. Today, she will speaking on the topic simulations as catalyst for sustainable smart cities. In this session, Yasaswini will share case studies and insights, her insight actually, on how energy modeling, microclimate analysis, and simulation technologies can inform early stage design decisions, and shape the future of urban sustainability. Please join me welcoming Yasaswini. It is your floor, actually. Thank you.
Thank you very much, Paulette, for the brief introduction on the topic and my introduction as well. I think you have set the ground for today's topic, and few things might be repetitive in my introduction as well. So I request everyone just please bear with me there. And first of all, thank you for IEEE Metaverse, IEEE YP, Young Professionals, and also IEEE Future Directions for giving this opportunity and recognizing us as young professionals and giving this platform to showcase our work. And thank you so much. Saying that, I will share my screen to start with today's presentation. Is my screen through?
Yeah, it is visible right now. Yeah.
Okay. So yeah, today's topic that I'll be going through is simulation as catalyst for sustainable cities. And I'm Yashasini Chilikuri. And before we go into fundamental understanding of what is simulations, what is smart cities, or even what is sustainable technologies, I would want everyone to picturize by the narrative of what smart cities look like, especially the sustainable smart cities, and look around our world, what is happening today in this area that we are discussing today. Why are we even talking on this subject today, and how is that our future might look like? So starting with the narrative, a day in the life of smart sustainable city. So I would request everyone to close your eyes and imagine walking up in a city where buildings don't just stand, but they breathe, adapt, and respond to your needs. The windows of your apartment tint automatically to block out excess heat, as the sun rises. You step out in a shade, street lined with trees that are planted not just randomly, but precisely based on microclimate simulations to reduce heat stress and improve air quality. You hop on public e-bus whose routes and timings are optimized daily using real-time data and sensors that monitor traffic flow, energy usage, and even comfort levels of passengers or public seated. As you walk to nearby any community centers, you pass through buildings whose facades change their shape based on the daylight control, and the smart grid uses renewable energy and adjusts based on the peak demand. And every drop of water that we used is reused and used efficiently. This is not just a science fiction, these are real capabilities. And these are the achievements that we can gain by the guided simulations using digital twins or sustainable technologies. They are already being piloted in many places that we'll see in the next slide. But how do these cities plan and build such environments? The answer lies in simulation. Simulation acts as a silent partner to shape these decisions before we lay each single brick. Few of the innovative global projects that are towards shaping towards our future of sustainable smart cities. I could just grab few of them, but I'm really sure there are many such. Starting with the first one, the Mustard City in UAE. They aim for zero carbon, zero waste city powered entirely by renewable energy. How is this possible? How is that they're doing it? Their innovation lie in solar energy integration, smart shading, and passive cooling designs. In another example of South Korea, a smart city built from scratch with integrated technology, and their innovation lie in centralized waste disposal. Singapore, which is transforming into a leading global smart nation, their innovation lie in nationwide sensor development and the AI-driven urban planning. In Netherlands, we see a different scenario where the smartest neighborhoods are planned with focus on sustainability and also community. Their innovation lie in circular economy principles. And in Japan, a prototype city is planned where testing autonomous vehicles, smart homes, and AI integration are tied up with innovations such as hydrogen-powered infrastructure. And in Brazil, as the picture shows in the bottom right, they focus more on the sustainable urban planning and public transportation using innovative steps such as BRT system, that is bus rapid transit. And they integrated these with the urban green spaces. So now that we have imagined and seen that what is happening around the world, now let's go into the technicalities, the fundamentals. So what is SusTech? The sustainable technologies. And why is it that used in our urban context or the green building plannings? So there is no single university standardized definitions for sustainable technologies as it is a multidisciplinary term, but few manage to explain. For example, the Oxford Environmental Science Dictionaries, they described it generally as technologies that do not deplete or permanently damage natural resources and that support long-term ecological balance. Whereas United Nations, they frame, while SusTech isn't explicitly defined, but the role of technology in sustainability is described as science, technology, and innovation. They are key drivers for advancing sustainable development. So it's not just a high-tech tools. It's about rethinking the way we design, build, and live in the cities. The key challenges that we see in urban development today, categorized in three, but I'm sure there are again more. The important ones are resource optimization, because the urban growth is rapidly growing and there are strains on energy, water, and land system, etc. We have to optimize them. and we have to reduce our higher operational costs and emissions. And there is lack of integrated planning that causes resource redundancy and waste. Another challenge that we see is climate resilience. Climate is it is very increasing to be vulnerable. We are facing extreme heat, flooding, and air pollution. This leads to urban heat island effect, which we'll discuss in the coming slides, that is UHI. And this existing in because of due to this, the existing infrastructure often lacks the flexibility to adapt to this climate variability. The third important challenge is the human-centric design. The citizens, they are often neglected for their thermal comfort, air quality, and accessibility. The disconnect between the designer and the actual user who experience it are not very much addressed. So marginalizing these challenges and also the communities that are facing inequitable access of green and health infrastructure. These are the major key challenges. So how can we use SusTech in addressing our urban development? So these are the few key pointers that can be highlighted what can be done for our sustainable smart cities using the sustainable technologies. The smart cities integrates digital technology with sustainability goals to enhance the quality of urban life. Therefore, the role of SusTech in smart cities lie in this point, that is the first one being the data-driven urban design. Through this, using simulations or sensors or digital twins, it makes evidence-based decisions across the planning and life cycle of the building. And resource efficiency, which is the major point, the development towards the low carbon or resource optimization of systems can help with the simulations or the sustainable technologies. Climate adaptive infrastructure, as we just discussed, our existing buildings are not adaptive. Therefore, using SusTech, we promote resilient design by simulating or responding to climate risks. Enhance livability, that is the human-centric environments. Humans should be able to live comfortably in their indoors, also outdoors, air quality and mobility and accessibility. Collaborative planning, that is the integrated design. The designers, that is architects or engineers and urban planners, and even the citizens of these cities should be able to play a role in the collaborative planning. So this is the role that sustainability smart cities would play and how the simulation matters in the sustainable smart cities. The key pointers are simulation will act as a design decision and by supporting as a tool. It also gives us early stage design interventions and efficiency and accuracy and collaborations. And why is this crucial in smart development? Because it helps us in many ways. Simulation is no longer just an analysis step, but it also becomes a real-time design companion. For example, performance, such as we simulate energy, daylight, and thermal comfort. These parameters makes us help us in deciding early challenges that we might face and how we can address them. And responding to microclimates, access to urban heat islands, wind flows, and outdoor comfort can be achieved, can be addressed through these simulations. And save time and resources is one of the key, that is the spotting of inefficiency. The earlier, the better, the more cost, say, effective results it may lead to. Digitally connected, yes, like there are a lot of seamless integration technology that is available today, such as BIM or GIS or urban data sets. So all these can be integrated in our design development. And what if scenarios? This is the very much key term that we can use using the simulations. We can predict we can design, we can trust, we can do the worst case, we can do the best case, we can do any test and compare the results of every design, however challenging the design is, however complicated the design is. So what if scenarios is always a question. Now we have answers to it. Therefore, ultimately, simulation isn't just a luxury, but it is a necessity or building future-ready sustainable cities. Few of the examples that I've taken before talking more on the tools, I want you to look at what tools can do. Then we can discuss on the tools itself. I'll starting with the building context and then moving to the urban context. So shading plus glazing. While this is an example of a room where the daylight is entering our building, and simulation tells us by a grid sensor form which areas are comfortable and which areas are not visually. When designing for high performance buildings, shading and glazing are two critical elements that can determine our visual comfort and also the energy efficiency. So the rule of thumb of designing windows are no more valid. With tools such as uh, simulation softwares, we can predict what can be our right window sizing. Using especially the solar diagram, the chart enables us to define what time the solar energy or the daylight is entering and what is the cutoff time we'll have to shade. So using the solar charts, we decide on the horizontal and the vertical or any form of shading devices. And there are few standard terms that we compare our results with. Here we have ASE, which is annual sunlight exposure, and UDI, that is useful daylight illuminance, and DA is daylight autonomy. Basically, ASE tells us if there is too much direct sunlight in a space, which can cause glare or overheating. Whereas UDI helps us identify zones that receive optimal daylight without artificial daylight. And the zones that are in gray tells us that how much shading is required and how much openings are required. Therefore, it gives us the balance of both. And daylight and autonomy shows how much of the year a space can function with natural light. So it is simulation of 360 days. So each simulation tells us differently when we are comfortable or when we are receiving enough light to do a particular task, and how much percentage of the hours or how much percentage of the days are we receiving a daylight. So this is the daylight simulations. And moving on to the energy simulations works a little differently. So there are few data gatherings that is required even for the daylight. But when we move to the energy simulations, uh, it becomes more complex because it's just not about the building geometry. We look at the lighting power density, equipment power density, that is the energy consumption by various sources, and the fresh air integration and what type of HVAC system we have, what is the flow rate of it, what the efficiency of HVAC system, and the temperatures or the ideal um, temperature and humidity that we would want to achieve in our zones. And also sometimes it is very much required, especially for existing buildings, to interview and understand how the user is actually occupying the building. So the simulation where we enter 9 to 5 for office building is not always 9 to 5. We know people start early. We know people go late sometimes from the office, or there might be some activity which is out of the schedule. So therefore, it is important to understand this what if scenarios and how much percentage of the year is this happening. And then we have our output saying what are the calculation, what is the consumption, and what is the HVAC system that is bestly suited for that particular design, and schedules that are mismatched. So what happens on that, due to that usage, what will be the energy difference? Therefore, this is for the new buildings, and for the existing buildings, there's another step of calibration. So calibration is something like digital twin building. The real building should able to mimic, sorry, the simulation building should be able to mimic the real building and should have the same patterns of energy consumption. And therefore, it's a very long process of designing the building itself and understand what happens at the site. The model should be able to predict, and then there will be a validation steps, and then the role of ECMs, that is energy conservation measures, play in. And therefore, whatever you want to experiment on the real building can be experimented in our simulation softwares. And therefore, the best one, the best strategy, or the best ECM can be implemented with the cost analysis. This is one of the example of the actual existing system, chiller plant or HVAC system, that was in an office building, which is a newly built building of around 2 to 3 years. And we tried to simulate the same HVAC system in our software. So of course, the building geometry plays a role, but here the HVAC being the high energy consumption equipment, we had to match the exact details of the site with our software. So the number of chiller plants, their efficiency, their inlets, temperatures, outlet temperatures, everything matters. And how many chillers are running at a time, and how many chillers are running during the peak consumption. Everything should be as per site. Once we get our model right, which has further more steps to understand how to get our model right. So this is one of our understanding of simulation, where the model usually gives us a system of auto size, and whereas in actual scenario we set the limits for everything to match the site and our model. We go with an iterations of inputting data. So when you input all the data at once, the software crashes and your data might not match to the existing data. Therefore, we went with an iterations, such as first identifying the type of system, second entering their data uh, with actual numbers, equipment by equipment. That is first the cooling towers, then chillers, and then the temperatures and the pumps and the variables and the set limits, etc. So on. So when we see a hike in energy consumption, we know something is wrong because we know what is the existing energy consumption. So we correct our simulation models to the existing, and the iterations are captured in terms of errors. Like the goal was to reduce the gap between the simulated energy use and actual utility. Therefore, both monthly and annually, the data was checked, and the statistical indicators, that is the standard evaluation method for calibration, is CVRMSE and NMBE, that is the coefficient of variation of root mean square error, and the other one is normalized mean bias error. As per ASHRAE guideline 14, it is acceptable to have CVRMSE below 15 and NMB within plus or minus 5%. So this is the data that we could achieve: the monthly energy consumption, the actual versus model. And now that we have our model ready with the limit that has been set for the error margin by ASHRAE, now we can tweak the energy conservation measures that can be implemented on site for the existing building. So all this is possible only with the help of the simulation softwares. So this is with the building where we have seen the daylight and the energy. And similarly for the urban context, we have a different metrics. So it's not just about temperature and humidity. There are other variations which are not controlled by our HVAC system. That is our wind patterns or the radiation that in the outdoors, which is very common where we are directly exposed to the sun. Therefore, UTCI is one of the key metric, which is Universal Thermal Climate Index, which gives us a broad temperature difference. And UTCI tells us how it feels like to people in outdoor spaces. It considers all the parameters that has been listed, and it makes a comprehensive thermal comfort index. And it is a scale of -50 to +50. And -50 refers to extreme cold stress, and whereas the +50 refers to extreme heat stress. The ideal temperatures are between 10 to 25. And this is usually used in urban context because of the urban heat island effect. So, which is also referred as UHI. What is this urban heat island effect? The urban areas tend to be warmer than surrounding rural regions, especially at night. This is due to heat retaining nature of built surfaces like our concrete walls and so on. Therefore, they lack vegetation, which impacts on higher energy demand and increased discomforts and heat stress and poorer air quality. Therefore, it is important for us to understand the patterns in the urban context in terms of all these external parameters, and the scale that we have is UTCI. And here are a few examples of UTCI simulation. And UTCI tells us the temperature, and it varies day to day. I mean, the time by paces in a day. So we have simulation here showing for morning, midday, afternoon, and night. So why are we looking at temperatures on different times in a day? For example, say suppose morning, which is 7 to 11 hours. This is where people begin commuting, or engaging in light activities. So therefore, the pathways have some solar exposure, and in cold and partial shading might be required in warm climates. Therefore, the temperatures usually in morning, it is ideally to be 15 to 23 degrees Celsius. I'm not referring to air temperature, but the UTC temperature, which is considered to be good. And if it's not in this range, then we have design interventions. Similarly, for midday, that is 11 to 13 hours, UTCI can exceed very drastically. It can go as high as 38 degrees Celsius, especially in dense and unshaded areas. Therefore, this period, it poses peak heat stress, and especially in tropical and arid climates. Therefore, the design interventions for this time can be dense shading using trees, canopies, or reflective materials, that is light colored pavements or uh, roofs, and then vegetation. Therefore, this will minimize the heat traps within the urban context. And in the afternoon, that is 13 to 18 hours, this is the time where solar radiation remains still high, but the residual heat also adds up. The residual heat comes from the buildings, which has been trapped earlier, that is in the midday. It starts emitting out. Therefore, UTCI may remain elevated even if the ambient temperature begins to decline. And the design intervention during this time is majorly with the building design, that is use the window to um, evaluate the material performance in retaining or releasing this heat, and implementing green roofs, cool roofs to reduce afternoon heat loading. And the public places, especially the playgrounds, should be fully shaded by this time. Therefore, it gives us the context of the building shade or the tree shade that is falling on the playgrounds should be ideally around this time. And at night, the UTCI might drop. compared to the afternoon, that is the midday and afternoon, it will be much lesser during this time as anticipated, therefore giving us some thermal relief. However, in UHI affected zone, it may still remain as high as 28 degrees Celsius. Therefore, the design intent during this time can be looked at in worst case scenarios to use permeable surfaces and vegetations to reduce retained heat, and design for nighttime ventilation, that is example, chimney effect between buildings, and avoiding any dark surfaces that may radiate heat even post sunset. Similarly, for the same urban context, we have solar exposure measure. This is another uh, not metric, but a different layer of usage patterns that we can see in the urban context. This simulation calculates how much direct sunlight a surface or space receives throughout the day or year. It is measured as percentage of sunlight time or hours per day that it faces. If there is too much exposure, it leads to overheating and glare. If it is too little exposure, it means there is poor daylight. Therefore, the challenge here is to have daylight and shading at a right point. And similarly, we have wind comfort simulations. So the wind simulations often use CFD, that is computational fluid dynamics. It tells us how wind flows through urban spaces. So here the map is showing for the positive, active, and uncomfortable winds. So positive means it is suitable for walking, sitting, or active use, and uncomfortable means windy zones that deter people or cause hazards. Therefore, our space can be designed accordingly based on the outdoor spaces that is required. It need not to be just ground always, it can also be the terraces. Therefore, here the terrace space of the buildings were also included in the simulations. And another last one that we have in urban context is the wind patterns. Like the previously where the wind that we have seen is whether comfortable or not comfortable, but this slide shows the direction. So why does this direction matters? Simulations will often visualize wind data in the form of wind rows. Here it is showing the predominant directions, and there will be usually the seasonal patterns as well. So the speed range here, it's showing a scale of low, medium, and high. Low is where it may cause stale air, discomfort in warm climates, and poor pollutant dispersion. And medium means it's generally comfortable and it can support natural ventilation and thermal relief. Discomfort, that is the last or the high wind, may cause discomfort and it may give wind tunnels. It may lead to wind tunnels and unsafe outdoor conditions. Therefore, it can help us in determining the design interventions such as low wind areas may be designed in such a way to enhance ventilation strategies by giving porosity in the building or courtyards or wind catchers. And in medium winds, it can be harnessed for positive cooling, and it is a great comfort outdoor area and can be used as is. And in high wind zones, it can call for wind breaks, therefore vegetation buffers or the podium level analysis for the pedestrians can be analyzed, and the design interventions can be given accordingly. Now, once the design interventions are done, there is before and after analysis for every design. So there is another tool which can simply do it very quickly. This is NVMet. And NVMet, it is a software simulation tool which understands how microclimate responds to different urban design strategies. This tool provides one key output, that is absolute difference in potential air temperatures. So this metric shows how the air temperature at pedestrian level can be lowered in some cases. The design interventions like tree plantation, green roofs, or cool pavements, or shading devices, or water bodies, when simulated, can show a difference. For example, the option 1, the green space with soil filling, was changed to option 2, green space with water body. So when this change has happened, the heat map here only indicates the temperature difference between the first option and second option. If there is a negative value, it means intervention reduce the temperature. In the design intervention has reduced the temperature, therefore providing a cooling effect. But if there is a positive value, it implies that the design might have trapped heat or it has disrupted the airflow. Therefore, it is a bad intervention. So for a quick decision making, uh, we have different tools, and for the detailed analysis, we have different tools. So when should you use and what? So these tools have evolved, and at different stages of design, it helps in different way. For example, at the concept stage, simulation help us understanding how massing, orientation, or building form will interact with climate. And it gives us a big picture decisions right from the beginning. And moving into schematic design, the simulations set some quantifiable sustainable goals, such as energy targets, daylight availability, or thermal comfort benchmarks. So in this stage, it's more about what we may achieve. But when we go into design developed phase, here the tools become more precise. We can test different materials and precise the HVAC system configurations, and the facade options for the building will be frozen. And also we can ensure that compliance of green building certifications. Even at the tender and execution stages, the simulation adds some value. These allow to validate design choices, and they also justify return on investment data. In some advanced cases, simulation can also extend to the post occupancy, where we can monitor the building performance in real time and track the particular data back into the future. And these are the list of simulation tools that can be used at different phases of the project, as we discussed earlier. And few are limited to the building design, and few are wide for the urban context. And few can be used for the early design decisions very quickly, and few can be used in a very detailed format. So all the details have been listed here. And the software that I have used for the energy simulation is the Design Builder, which is by Energy Plus. And the daylight simulations are usually in Rhino with Grasshopper. And the SimScale is one of the best tool for the energy simulations or even the CFD simulations, but it's not an open source. And NVMet, we have seen how it can simulate in microclimate and also show us the temperature differences for each design interventions. Now we have the tools. Okay, how it can be integrated. There are many tools, and each tool does each way. Each tool gives us each prediction. But it is always key to understand. It is very smart to design sustainable smart buildings with a smart platforms. For example, BIM platforms, they serve as single source for the geometry and documentation, which can be collaborated with the simulation plugins. Uh, Therefore, it can allow real-time energy and daylight simulations and also the thermal comfort assessments directly within the BIM software. And the cloud collaborations, that is BIM 360 or ACC, Autodesk Construction Cloud. It enables the designers to collaborate in real time, therefore reducing any delays. And this also can be collaborated with the analysis tools. Therefore, the high accuracy simulation tools can export data in high accurate time without wasting time on modeling. And without the softwares, without the simulation help, the challenges would remain as is. That is, buildings might go with higher operational energy use and over dependence of artificial light and poor thermal comfort or ventilation and oversights in urban climate, because the microclimate is not usually taken into consideration when designing a building in city. It is used in a large scale of that country or that city data, but microclimate plays a lot of difference in design interventions. And of course, we might end up paying increased cost, and without this design interventions, there we cannot experiment on any design iterations. Yeah, that's it. And the road forward is for this simulation-based learning is the digital twins of cities, where we can do the real-time simulations of every minute. Data can be interpolated or every hour to decrease the burden of over heavy data can be interpolated, and the energy use patterns can be taken out. Any mismatch in energy use between the real building and the real-time simulation can help us identify the errors very easily at that given particular point in time, without waiting for months to analyze where and what is actually wrong. And community-driven simulations, it's not just the designers, we engage the actual users, that is the citizens, and we ensure they get the uh, actual comfort for the cities that they're living in, and it can be tracked by taking a real-time feedback from the citizen itself, and also interpolate them with the sustainability metrics. And scalable learning platforms. So it is the simulation based through web tools, that is immersive. This is more advanced, where we can open to the VR or AR, the virtual reality or the artificial reality, and the gamified learning for the young professionals. This has been already in labs where the students can actually go into a experimental lab and experience what is happening, what happens when our HVAC system is not very efficient. You can turn off the efficiency and look at the energy consumption in the real time using these tools. That's it. Thank you. And my details are given below. If you have any questions, you can drop in the chat box. I'm open to questions. And if you need some discussion or any project that you're currently working on and you would want to discuss, you can mail it to me as well.
Thank you so much, Yashaswini, for that kind of great presentation. Actually, that's a inspiring and engaging presentation.